We have two topics for today, and I hope that we actually discuss both of these topics. And the first topic is confidence intervals. And it is the following story. As we discussed previously, we can use data that is obtained from our sample to estimate some properties of population. So basically, we have something like a large box with balls, and we have some numbers on these balls, like um, length of sentences in some language or height of people in Moscow. So here are some numbers. And then we do our sampling procedure. And then we have sample. So we have a sequence of numbers. Something like this. And we have a sample size that is usually denoted by letter n. This is sample size. And as we discussed some time ago, actually this is the central idea of everything that goes on in statistics, is that we can use this sample to estimate some properties of population. So we have sampling procedure from population to sample that generates our sample, and then we have an opposite arrow where we say that we do a thing that is called statistical inference. For example, we can use sample to estimate properties of population. And basic example of this reverse arrow is a problem when we want to estimate population mean. So we have some, let mu be population mean. And we can use sample mean. So just arithmetic average of the numbers that we have in our sample. Let me denote this sample, for example, by letter X. And then we have sample mean that I denote by X bar. So this is just this is sample mean. And as we discussed several lectures ago, we know that this sample mean can be used as an estimate, as an approximation of this population mean. So that means that if our sample is large enough, then sample mean, so this value should be close to this population mean. So this is law of large numbers. That says that X bar tends to population mean as sample size tends to infinity. So for large samples, we have good approximation. And so we want to use X bar as an estimate for mu. So what does it mean? It means that, for example, we are interested in average height of people in Moscow, and we don't know this number, but instead we have a sample, for example, of 1,000 people from Moscow, and we measure this 1,000 people, and if we believe that these people were sampled just randomly from the population, or using the procedure like this, like random sample, then we can use just sample average as an estimate for the population average, population mean that we are interested in. But after this discussion, we have a new question. Okay, let us assume that I have some research, and I know that we obtained some numeric value. So assume that we conducted this research, and obtained some estimate like X bar equals to 153. Just some more or less arbitrary number, but assume that we obtained this number from our research. So that means that we have some value that we are interested in. For example, this is height of people. And we have our value 153. This is our approximation. This is our estimate. And after that, on one hand, I know that this is estimate that is in a sense good. That theory suggests that this estimate should be good at least if I have large sample size, if I have enough elements in my sample. But after that, I have a natural question. Okay, I understand that this is my estimate, but where is real value of mu can be placed on this line? I understand that it should be placed somewhere near that it is most probably somewhere near this value 153. This is my observed value. But can I say something more that it should be somewhere near? Can I make some quantitative conclusions about where this value can be located? In other sense, I'm interested in how precise my estimate is. So, how precise this estimate is. Or in other terms, where my real population mean is located how far can it be from my estimate? So let us assume that I have, for example, 0 here. Is it possible for my real mu, for my real population mean to be located somewhere here or somewhere here? Or should it be located somewhere here or somewhere here? So this is the question that I'm interested in. I want to estimate precision of my point estimate. So is it clear what I'm going to study? What is the question that I want to answer? Are there any question at this stage?
So X bar is the mean of height, yes, somewhere.
It is our sample mean. Yeah, we assume that we get a random sample from our population. We denote it by X, and X bar is our sample mean. So we just, for example, we have 10 people, and we just measured them and obtained our 10 numbers, and then we get this sample mean. And we are interested in what is the possible distance between the sample mean that we obtained and the actual population mean, so mean height of all people in Moscow. What is the distance between these two values? This value, we don't know this value. We want to estimate it.
Okay, I see.
Mhm. But we know this value, and we understand that they have to be more or less close to each other. But what is we are interested now is how close they are, or how far. Okay. So now, actually, what I want to do is something like this. I want to construct some segment and say that the actual mu, the actual population mean, should lie inside this segment with some probability. This is actually a rather tricky construction, but let me try to explain it. It is not very complicated, but it is about tricky in the interpretation. And again, to introduce this construction, I have to introduce imaginary experiment. In this story, we do our estimation only once. We have only one sample, and from this sample we find sample mean and put a point on this line according to this sample mean. But now let us pretend, let us imagine that we repeat the same experiment a lot of times, like 1,000 times or 10,000 times. Let us imagine that we repeat this experiment. I mean that we make a sample and find sample mean. For example, 10,000 times. And we obtain 10,000 sample means. what can you say about their distribution? So it will be, we will get some distribution. So we will get some a lot of points on the straight line as a result of this experiment. This is an imaginary experiment, but can you tell me something about this distribution, the distribution of sample means, if you repeat sampling from the same population a lot of times?
Well, it will actually be the normal distribution.
Yes, concentrated near what value?
Near the actual sample mean.
Exactly.
I mean, the mean of population.
Exactly, the mean of population. Yeah, this is absolutely correct. So basically, if I draw a histogram of these 10,000 numbers, then I will get something like this. So I get, I have some actual population mean, and my sample means will be located, will be distributed around of this actual population mean. So this is my real population mean. In fact, I cannot draw this picture in my experiment. This is a purely imagination, because in fact, I don't know this mu. So I don't know where this graph will be located. So, okay, let me use different color here just to distinguish between two kind of points. This is my real population, and I have some points. And in fact, I can calculate some properties of this normal distribution. In fact, I don't know the exact location because I don't know mu, but I can find some properties of this normal distribution. First of all, I can find its standard deviation, so I can find how wide this distribution, or in other sense, I can say how far I can get my sample mean from the actual population mean. And this actually can be found. And let me say that standard deviation of sample means actually it equals to standard deviation of population and you have to divide it by the square root of n. So what does it mean? It means that as you increase n, as you increase your sample size, square root of n is also increased. And so this picture becomes more concentrated near the actual population. So this is actually an exact formula, but we don't we cannot use this formula because we don't know this standard deviation of population. But again, we can replace standard deviation of population by our estimate of this value. So we can say that this is approximately equal standard deviation, sample standard deviation. And we can use this formula to estimate how far our points can lie, how far can they be from this population mean. In fact, this value is called, this thing is called standard error of mean. So this value shows, so this is called standard error of mean because it shows how far our sample mean is from the actual population means. So it means that what is the size of an error that we will make if we replace our real population with the sample mean, real population mean with sample mean. So this is called standard error of mean. It decreases as sample size growth. And for a given sample, we can find the value of this standard error. And then we can use this graph, we can use this normal distribution to construct the confidence interval. This is done in the following way. First of all, let us pick some value that is close to 1. Um, so let us pick a value that is called beta. For example, let us use 95%. I need value beta to be close to 1. And then I do the following thing. I look at this. I look at this graph. I don't know exactly where it is located, but it doesn't matter now. Anyway, I will draw the following picture. I will put here and here. So this is mu. Let me put here mu plus 1.96 times. Okay, let me use some shorthand notation. Let me denote this value by just S. So I put here 1.96S, and I put here my mu minus 1.96S. And if I do that, I can guarantee that the probability to obtain the value inside this segment is equal to my beta. So this is 95%. So in fact, this magic value 1.96 is connected with this value 95%. If I change this 95% to, for example, 99%, then I have to change this value. So this value is found by using this value and some properties of this normal distribution of this curve.
Can I ask a question?
Sure.
I think I missed what does the 95% stand for?
Just a second. I just pick this number more or less arbitrarily, and I want to construct such a segment that probability to obtain sample mean inside of this segment should be equal to at least 95%. So I want to obtain such a segment that more or less almost surely I will be inside this segment. So to ensure it, I just pick this 95% as just a representation. What do I mean when I say that this should happen almost surely, almost every time?
Thank you.
Mhm. So this is actually a theoretical construction, and actually I cannot find these values because I don't know mu. I can find S. S is constructed just by my sample. So if I have sample, I can find sample standard deviation, and I know sample size, so I can find this value. This is simple, but I don't know mu. And everything here is, in a sense, purely theoretical. But now let me return to my actual research. In my research, I have some numeric value that I obtained from my sample, this estimate. Let me put this estimate somewhere. For example, it is somewhere here. So this is my X bar, sample mean. And now let me do the following thing. Let me plot a segment around of this X bar, which length is given by this S. Not actually S, but by this value. So let me redraw this picture once again. I have mu. I have this normal curve around mu. And I have this segment. And now I have my actual value, X bar. Let me use additional axis just to avoid clutter. So this is the same X bar. And now let me draw a new segment. This segment is X bar plus line 0.96s. And here I have X bar minus 1.86s. So in fact, on this picture, I draw only things that I can draw. Everything here I can find. I can find X bar and I can find S. And now I ask the following question. What is the probability that mu lies inside of this segment that I constructed? If I repeat the construction a lot of times. So my question is the following. Again, I can repeat my experiment several times, actually 10,000 times, and every time I will get a new segment. For example, I can obtain value of x bar somewhere here, and I will get segment here. I can obtain x bar somewhere here, and I will get segment here, and so on. So my question is, how often I will get that mu lies inside of this segment? So if I will repeat my experiment, I will get different values of x bar. And these values of x bar will be distributed according to this law. And then my question is, how often will I get such segment? So for each x bar, I will draw its own segment. And my question is, how far will I get segment that will contain this value mu? Let me draw it once again to make my point clear. I have value mu here, and I have here mu minus something, and here I have mu plus something, and then I get some value x bar, and I have x bar minus the same value, and here I have x bar plus the same value. So I have this segment, and I ask you how often mu will be inside of this segment. Is it possible that mu is outside of this segment at all? Where x bar should be located to allow mu to be outside of this segment?
It's not possible, I guess, because then x bar should be located outside this mu plus minus
Yes, but is it
interval.
possible? Yes, is it possible?
I think no.
Why?
Oh, I see. It's not a yes. Sure.
So is it possible for x bar to be somewhere here outside of this segment? And if possible, then what can you say about probability of this event?
It's possible, but will only meet really rare.
Mm-hmm. Yes, it is possible, but probability of this event is less than 5%, because we demanded that 95% of probability, so probability to be here on this segment is 95%. So probability to be outside of this segment is less than 95%. No, sorry, is less than or equal to 5%. Right? We are either here or here, so sum of probabilities should be 1. So, and if I look at these two pictures, I see that the condition that mu is outside of this segment can be restated in the following term. So actually, you can just look at this picture and see that if x bar is inside of this segment, then mu is inside this segment. Just because the condition that x bar is inside of this segment means that the difference between mu and x bar is less than 1.96s, and this is the same condition as to say, so basically three conditions coincide. Mu inside this segment, x bar inside this segment, and the distance between mu and x bar is less or equal to 1.96s. So these three conditions are just equivalent. Right? Everybody agree with that? And so if x bar lies on this segment, then it means that mu lies on this segment, shifted. And by construction of this segment, we know that probability that x bar lies on this segment equals to 95%. Just because we chose this value, this coefficient 1.96, we chose it in such a way that probability that when we find this sample mean, we will get a value on this segment is 95%, just because we chose this length in this way. So it means the following way. It means the following thing, that if we construct our interval, our segment in this way, so we get our sample mean, and then we put two values to the right and to the left from x bar that are calculated in this way, then we can be sure that probability that this segment contains mu equals to 95%. So probability of these events by construction of the first segment. And in fact, segment that we constructed, this thing, is called confidence interval for population mean with 95%, how it is called, confidence level. And this is how it works. So now we provide not only some point estimate, but we provide some interval, and we say that this interval, okay, more or less, almost surely, under some condition, will contain our actual population mean. Are there any questions so far?
I have a question maybe. So why is mu inside X bar interval? Could it be the case that we have such, I don't know, extreme sample that it does not coincide with the mean of the population? So I understand why the mean for the sample should be inside the interval for the mean of the population. But is it always the case that the mean for the population is inside this interval for the mean of the sample?
Yes, because actually these three conditions are just equivalent. Actually, these three conditions are just the same condition. We can say that mu is inside of this interval. It means that mu is somewhere here. Sorry. If mu is inside of this interval, it means that mu is somewhere here. It is to say this is the same thing as to say the distance between mu and x bar is less than this radius, right?
So we can't imagine a case where it won't be possible.
It is possible. It is possible that we get x bar somewhere here. We construct our confidence interval. It is somewhere here, and it doesn't contain actual mu. It is possible. But what we say is that the probability of this event is small. We don't say that it is completely impossible, but we just say that in most of cases, our procedure, the procedure of the construction of this segment, will give us a reasonable result. Reasonable result, it means that mu lies inside of this segment.
Okay, so as I see, we can always judge by our population, our sample, and vice versa. So there.
Well, not always. Well, from practical point of view, we have to do it because we don't have anything else. We don't have any more information about our population other than we can take by analyzing some sample from this population. This is our general problem. And again, every time when we do it, we can make a mistake. It is possible for us that we do our experiment, we construct this confidence interval, and this confidence interval, in fact, does not contain the value that we are trying to estimate. It is possible. What we are trying to do is to control the probability of this kind of mistake.
Okay, and what should be the minimal size of such samples that we can judge the population with the 95% confidence?
Well, actually, this is a good question. I'd say that even not very large population, even not very large samples will work. In fact, there are two parts of this question. One part is that this whole construction relies on the fact that sample mean is distributed under normal law. This works for more or less arbitrary initial distribution of the population for large samples large enough. Actually, not very large. I believe that 100 items is enough. And then, in fact, after you have your central limit theorem, so after you have this shape of this distribution of sample means, actually the rest works automatically. I mean that, let me ask you a question. What happens with the length of this confidence interval as you increase sample size? What happens with confidence interval? If I just get more data, will it increase or decrease?
It will increase, no? Because I don't know, if you have larger sample, it is closer to the population.
Yes, but if it is closer to the population, it means that, okay, if I have, for example, I have two curves. One curve corresponds to small population, sorry, small sample. And another curve corresponds to large sample. And if you, okay, let me use different axes to draw it. So if you have, I have mu here and mu here. If I have large, if I have small sample, and here I have large sample, if I have small sample, it means that the values of our sample mean can be rather different from mu. And so to ensure that I have 95 probability that mu lies in interval around this point, around my x bar, I have to draw some segment like this, right? And what about large sample? What changes here? If I have large sample, it means that my values of my sample mean lie somewhere near mu. What does it mean from the point of view of confidence interval? What happens with confidence interval here?
Smaller.
Yeah, it becomes smaller. In fact, this is natural because now you can be sure that you are close enough to mu. And so even if you put small confidence interval around of your point, most probably you will catch your actual population mean. So the larger, the more data you have, the smaller confidence intervals you have, because confidence interval reports how large your errors are, how large errors you can expect.
I would like to add that it can be easier to think about confidence intervals in terms of like real confidence. Like if you don't know what's happening in the world and you don't know and you asked about some things that you really don't know, you can say like, what is the weather today? And the weather is really volatile and it can be snow tomorrow, or it can be very warm. You can say it's like from -30 to 30. And you have really large intervals when you're not sure. When you have more data, you can say, okay, tomorrow will be something like +5, ±2. So with larger confidence, you have lower intervals, and with larger data set, you have higher confidence.
Yeah. Thank you, Ivan. Yeah, this is absolutely correct idea to think about this confidence interval. Like indeed, you say something like that the value that you're estimating lies from this to this value. So, and this is actually the correct everyday interpretation of how this confidence interval works. Actually, Ivan posted a very nice link to visualization of these confidence intervals. Let me try to show you. Yeah. So in this visualization, you generate a lot of samples. Actually, you can think that you do a very similar experiments. For example, every second you do a new experiment with the same population. So, for example, you have several thousands some companies that do the same research, the same kind of research, similar research. And all these companies provide their own data, they get their own data, and they provide their own results, their own confidence intervals. And in this case, our sample mean is just 0. And you see that you have different actually sample means. They are large blue dots, and around of each sample mean you have confidence interval, and most of this confidence interval contains the actual sample mean, but some of them do not contain. They are shown in red, but you see that even in the cases when they do not contain the sample mean is somewhere nearby. It is more or less impossible to get sample mean that is too far from the population mean. This is possible, but the probability of this event is very small. And you can change some properties of this procedure. For example, you can change your confidence level. Let us try to guess. What happens if I increase confidence level? For example, I will consider not 95% confidence, but 99% confidence. What happens in this case? What happens with the length of confidence intervals? Any ideas? If I replace 95% with 99%. So it means that I want to be correct in 99% of cases and not 95% of cases. What should I do with my confidence interval to achieve this better confidence level?
Yeah, you should move a black button to the right, and then you will see. Yeah, but actually, I don't know if it is fair to do this, but I did this, and as I see it now, I have just one missed in out of 100. So it
Yes,
it
but what happens with the length of confidence interval? Should confidence interval become larger or smaller if I increase confidence level?
smaller. So as I understand, if you have much confidence, you have less confidence interval. Is it correct?
Actually, there are two possible ways how to interpret confidence. If I want more confidence intervals, sorry, if I want to get more confidence level and I have the same data, then what should I do with my confidence, with my length of confidence interval to make sure that I have increased confidence level? Okay, let us try to do it. You see that I increased confidence level and all my dots are the same. I have the same data and the same process that generates this data. But I want to make more of my confidence interval to be good, to contain the actual sample mean. So it means that I have to increase their length. So in a sense, to make less mistakes, I have to increase my length of confidence intervals. For example, if I try to predict tomorrow's weather, if I want to if I want to be correct in with confidence 95%, then I can say, okay, I think that tomorrow's weather will be from I think from 5 to 15 degrees of Celsius. But if I want to be 100% sure that I will be correct, or 99% sure that I will be correct, I will say something much more wide. I say, okay, I think that tomorrow's weather will be from negative 50%, sorry, from, let me write it down. So predict tomorrow's weather. I'm not a meteorologist and I don't have a data actually, but I can just look at window and look at my thermometer outside, and I can say that according to what I see now, I have 95% confidence that tomorrow's temperature, tomorrow's day temperature will be inside interval like from 5 degrees Celsius to 20 degrees Celsius.
So is it always that the larger confidence level, the larger is interval?
Yeah, it is provided that you have the same data. Of course, actually the length of confidence interval depends on the data that you have and the confidence level that you want. So in this case, I do not collect more data, but I want to create a forecast that will be of better confidence. I want to decrease probability of my mistake. To do it, I will say, okay, under this confidence level, okay. Let me. I will be more cautious, and I will say that it will be from negative 20 degrees Celsius to 30 degrees Celsius. I'm sure with 99% confidence that our tomorrow's temperature will be like this. And I can be a bit more riskier. I can decrease my confidence level. And I can say that, okay, in my opinion, tomorrow's temperature will be from 10 degrees Celsius to 15 degrees Celsius. If I'm very risky, then I will be incorrect in 50% of my predictions, but I can provide very small confidence interval.
I don't see the last line.
Oh, this one? So this is the idea behind these confidence intervals. So with 100% confidence, I can say that tomorrow's temperature will be from negative infinity to plus infinity. 100% guarantee. So there is a trade-off between not making a mistake and saying something informative. Actually, we are interested in small confidence interval usually, but we have a trade-off like this.
So that was I thinking about, that the larger confidence interval, the more useless data we have. That's why we actually are doomed to have less confidence interval.
The more data we have, actually, if we increase data, let me return to formulas. If we increase the amount of data, then we increase this number n, sample size. And it means that in this formula, we increase the denominator. And it means that this s becomes less. And this shrinks our confidence interval. With more data, we can make more precise predictions, more precise estimates. So more data, larger n, smaller confidence interval, more precise estimate. Okay. Okay. Then, in fact, I have 15 minutes. And in these 15 minutes, I want to discuss the second topic of my lecture. And this is related to the notion of correlation. And what is correlation? Let us assume that we have two numeric variables. For example, you have something like, okay, let me use example that I can understand. Assume that you have several students, for example, in high school, And each student have their grade on different subjects. And for example, you have reading grade, and you have like math grade. And then you have a table like student reading math, and you have some values here. And so on. And you can visualize this table as a point cloud. This picture is called scatter plot. You can just put every row of this table into our picture in the following way. You just put, for example, here is 71 for reading, and here is 41 for math. And so you have a point here. And after that, you can visualize all the rows of this table. So each point here is one student. For example, this is student A, and you will get student B somewhere here, and so on. And after that, you can look at this picture and try to understand, are there any relation between these two variables? For example, let me try to draw some possible relations. Let me use just abstract variable names x and y. And let me ask you, what can you say about the relation between x and y? This is picture number 1. What can you say about the relation between x and y? When I ask about relation, I mean an answer on the question like this. If I know that x is large, what can I say about y? So if I see this picture, if I know that for some particular student, for some particular data point, I know that the value of x of this data point is large. So we are, if I look at the horizontal axis, I'm somewhere here. What can I say about values of y at this picture?
So if x is large, so y is also large in this plot.
Yeah, we see from this plot that if x is large, so we are basically somewhere here, and it means from the plot that we are somewhere here at the image, and we see that for these points of our data set, we see that the corresponding values of y are also relatively large. They are larger, for example, at this part of the picture, values of y are larger than at the opposite, at this part of picture. So the answer is y is also large. Of course, when I say large, small, it is just something relative. Here, when I say that x is large, it means that it is near maximum of all values of x. And if I ask, for example, if x is small, it means that it is somewhere here, near minimum of all values of x. So So my statement about this picture is that if x is large, then y is also large. Let me draw another picture. What can I say about this picture? Again, the same question. If x is large, what can we say about y? Let me even change this picture a little bit just to make sure that I do not introduce some misconceptions. Let me assume that I have this picture. What can I say about values of y if x is large?
Not so much, because we can see that when the x is large, there are 3 possible dots for this or more for y. So
Yeah, actually we
nothing.
have, actually, as I said, everything is relative. So when I answer the question, oh, what happens if x is large, I have to compare it with the case when x is small. So here I just say that here is x is large, and I have to compare it with the case when x is small. And x is small, it means that we are somewhere here. And in this case, we have these points. So here is x is small. And can we say that we see some natural difference between these points and these points with respect to this y variable? Can we say that y is larger here than here, or vice versa?
It seems that there is no correlation.
Yeah, we see that variable of y more or less doesn't change when I change x. So I consider large x, and the values of y are like this. And I consider small x, and values of y are more or less the same. So in this case, nothing can be said. Everybody agree? Okay, then let me construct another picture. Something like this. What can you say about this picture? Again, the same question. If x is large, what about y?
Y is small.
Yeah. We see that here, if x is large, then at the same time y is small, and vice versa. If x is small, then y is large. So here is the opposite dependence. Here we see that if x is large, then y is small, and vice versa. So this is, in a sense, opposite to what we've seen at the first picture. And finally, let me ask the following question. Let me compare two pictures. Hmm. Where the relation between x and y is more obvious, more strong, on the left picture or on the right picture?
On the left.
So the relation is stronger on the left. So here. Everybody agree with that? At least if I ask where it is more obvious, it is easy to see that it is on the right, on the left picture. So actually, the idea of mathematical notion of correlation is to construct some value that allows one to measure this idea of positive or negative relation between variables and measure how strong this relation is. And to do so, people use the following formula. Actually, this is called Pearson's correlation coefficient. So let me draw how this correlation coefficient works. Let me draw some data set. I have the following formula. This Pearson's correlation coefficient is usually denoted by small letter r. And it goes in the following way. First of all, I will consider not value x and y, but I will shift my axis in such a way that this picture will be drawn at the center of my axis. So I just put here value x bar, just average of all values of x, and I put here value y bar, and then I will consider difference between coordinates of my points and x bar and y bar. And then let me, first of all, let me introduce another function that is called covariance. And this covariance is calculated like the following. I pick some point, xi, yi. I find the difference between xi and x bar and yi and y bar. So let me pick some point. For example, let me consider this point, this point. What can you say about the sign of this product? So x bar minus xi minus x bar in this case. What can you say about sign of this difference for this point? This is point I.
Positive.
Yes, it is positive because actually this is the distance like this one. And what about this thing? What about the second term? So this difference is xi minus x bar, and this difference is yi minus y bar, and both of these differences are positive. So their product is positive for this point. And what about this point, for example? What can I say about the corresponding product for this point? So what about xj minus x bar? Let me denote this point by j. What about xj minus x bar?
So it is negative.
Negative. And what about yj minus y bar?
Also negative.
They are also negative. So the product is positive. Are there any points at the graph that I have where this product is negative?
Okay, so we should find minus and plus. So we should find, for example, the point where xz minus x bar is positive and y, I don't know.
Can you just
YB?
peek at this? Can you peek at some point at this picture? Where should they lie?
If, for example, the second quarter clockwise, what do we see here?
Yeah.
So
in fact,
it will. Yeah, so x will be positive, yes, and y will be negative.
In fact, these 2 points give us a negative contribution. So here are negative. And these points, all these points, will give us positive contribution. And you see that if I find the sum of these products, so if I consider something like this,
So it will be 0.
Why do you think it will be 0?
So because I don't know, it should be the same because we have two negative sums in the first and third quarter, and two positive sums in the second and fourth quarter.
But every point at this picture corresponds to one term in this sum. So we have a lot of terms that are positive. These ones.
Yeah. So here it will be positive.
Yeah, it will be positive, most surely, because we have only 2 negative points here, and a lot of positive points here and here.
Yeah, but if we would have so if we would have equal amount of points in each quarter, it would be 0. Yes.
Yeah, exactly.
Okay.
Exactly. And in fact, this what happens if you don't have any correlation, because in this case you will have something like something symmetrical, more or less, something like this, and you will get positive points here and here, and you will get negative points here and here. And then positive points will compensate negative points, they will cancel each other. So everybody understand how this picture was constructed and how this covariance sum of products, actually covariance is this thing. Probably after probably you have to divide it by something. So let us divide it by n. This thing is called covariance. Yes.
In what situation it can be applied? When do we need to understand this?
Well, it is a rather natural case when you're interested in the relation between 2 numeric variables. When you are trying to answer the question like, what happens if you find that one value is large? Does it mean that you have some new information about the other variable? Is it true that languages with large number of letters produce smaller length of sentences, something like this? If you're asking about the research questions that can be, if you're asking about the research question that can be answered by this notion of correlation.
Can you remind what is Y? What is I?
This I is just number of some element here. So I just say when I write this formula, I just say the following: that I pick some point on this graph. You can think about this graph as, let me return to the beginning of this story. We had students, and we had their reading and mathematical grades. So every point here is one student, and we are interested in the relation between their grades. Is it true that people who read better, is it true that they also do better at mathematics, or these two variables are not related? So what I say when I write this formula is the following: let us pick some student, and for the student find this product. So for example, my horizontal axis is reading, and it means that I will find the difference between the reading score of this student and the reading score of average student, so average reading score. And on the same, and this will be this part of this product, and the same thing with, for example, math. Right, so every point here is one student, and for each student I find this product, And then I find the sum of these products for all students. So for each student, I write this product and write their sum.
Mm-hmm.
And then we see that those students who are both better than average on both reading and math, or who are opposite, who are both worse than average on reading and math, they give us positive contribution to this sum, uh, because this is a product, and in both cases this product is positive. And so we see that if we have this relation, if indeed people who are better at reading are also better at math, we see that most of points will be green. They will contribute with positive contribution to this sum. And those points who will contribute negatively will be rare in this case for this kind of picture. So we can say that this covariance is, in a sense, can be considered as a measure that measures this relation, this positive relation between reading and math. So if we see that it is positive, then we can conclude that we have some positive relation between reading and math.
Okay, xi and y is like a real score, and y bar.
xy is like reading score,
Mhm,
reading score of ICE student.
mhm.
So you just enumerate all students, and this is what xi stands here.
And y bar, for example, it's the mean of their scores in maths.
Yes, exactly. Actually, yeah, this is mean, and this is mean reading score, and for y, this is the same thing. This is mean math score. Yeah.
Mhm. Okay, I see.
Mm-hmm. Actually, what is actually used as correlation coefficient is not a covariance, but in a sense normalized version of this covariance. To find R, you have to divide your covariance by the product of let me think, the product of standard deviation of x and standard deviation of y. So this is a rather huge formula, but what is important to know about this correlation coefficient? This is actually what is called Pearson's correlation coefficient. And it is known that R is from -1 to 1. And if you have R that is greater than 0, then you have something like this. So we have positive correlation. The larger x, the larger y. If you have R that is less than 0, then you have negative correlation, something like this. And if you have R that is equals to 0, equals to 1, then it means that you have linear relationship, just perfect linear relationship. And for -1, perfect negative linear relationship like this. So the closer R to 1, the closer the corresponding point cloud to the just a straight line. And this is what I want to tell you about correlation coefficient. There is a funny game when you can practice at guessing the correlations. Actually, this is called guessthecorrelation.com, and you can play a little bit this game just to make sure that you have some intuition about this correlation. It is actually a good a good thing to be able to estimate, just visually to estimate the correlation coefficient. And I think that's all with today's lectures. More questions about correlation or confidence intervals?
And what's what's the difference between covariance and correlation? So I just saw it, but
yeah, in fact, the main difference is that correlation coefficient is, well, how to say it? If, for example, if you rescale your data, for example, if you multiply all values of x by 10, then covariance will be also multiplied by 10. So covariance is something that is measured in the same actually it is some value that doesn't have any universal interpretation. If I have a correlation coefficient and I know that it is close to 1, then I understand that it is very large. I understand that my relation is close to this perfect linear relation. But if I know that covariance is, for example, 100, I know nothing because I don't understand is it large or small, what is 100. So this is why we normalize this covariance by dividing it by the standard deviation of x and y.
okay, so there could be a covariance between two unrelated subjects, but if there is a strong correlation, then it means something. Yes.
Well, I just cannot interpret the value of covariance if I just know this value. I cannot interpret it. I have to compare it with standard deviation of my variable, because okay, I can say you that covariance between your two variables is equal to 1000. Is it small or large? Well, it depends on the units in which you measure your variables. For example, if one unit just the range of one unit is from -million to +million, then covariance that equals to 1000 probably not so large. But correlation coefficient is unitless, so you don't have any units of measurement here, because all units of measurement will cancel each other. So this is this can be interpreted just with some.
What is a SD in the formula?
This is standard deviation of the corresponding sample. So you have a table like this, and you can consider one column of this table as just a collection of numbers, just like you have a sample, and you can find sample standard deviation. Sample standard deviation is the square root of sample variance, and sample variance, let me recall that sample variance this is something like something like this. So you find a square of the difference between each element of your sample and the corresponding mean, and sample standard deviation is just a square root of sample variance. So this is basically just some measure of statistical dispersion, measure that measures how far your values are from the corresponding average value.
So, and if we apply this formula for R, we can't have R which is more than 1.
You can't. This is a theorem. We can actually prove it, but we don't need to. We can just believe the mathematicians that they have a proof.
But by X and Y in this formula, we...
These are two samples. These actually are two columns of the table, like this. So I just denote the full column just by one letter. Just this column X and this column is called Y.
Just the result we have, the data.
Yes.
For example, 71 and 65.
No, X here in this formula, X is the whole column. For example, I have X, Y, and I have 21, 32, 51, and Y, I have 25, 31, 52, something like this. So covariance of X and Y is calculated using this formula. So, for example, how many, if my data is given by this table, how many terms will we get in this sum? How many terms of this kind you will get in this sum for covariance?
3.
For this table, three. Yes, exactly. So this is what's shortly denoted by this covariance of X and Y.
And when we speak about standard deviation, it's standard deviation from the mean. Yes.
Yes, it is. It is in any case, any of these kind of deviations, standard deviation or variance, it is a deviation from mean. Exactly.
Okay, thank you.
Okay, more questions? So we can probably make a 10 minutes break and then continue with practical lesson.
Yep, okay, let's start 8 and 6 minutes, something like that.
You can play guess the correlation in the meantime.
Yeah, we can actually play it together.
Yeah, it's fun. I like the game. I like its style. That it is just like 8-bit games of my childhood. Okay.
So, hi everyone. It's nice to see you again, and let's really start with a playing game. So, who tried this game, with the correlation game? If nobody, you can try to do it by yourself. Do you have the right to show your screen? If you're brave enough, you can play and we can see how it works. So who is brave enough, please? Come on, guys. Don't be shy. It's a seminar. It's okay if you do mistakes. It will be pretty fun, actually. You will lose hearts. So who is brave enough? Okay, if nobody, I will do it by myself. Okay, let's start the game. So do you remember what is a minimal and maximum value for correlation coefficient? Come on, guys, I need to hear you.
1 and -1.
Yeah, -1 is a minimum value and +1 is a maximum value. Meaning that if you have +1, if it's something like you have dots along the line. So what do you think about this situation? Just guess some number for this. Actually, in this game, it's a bit limited because you don't have negative correlations. It's a pity because correlations can be negative too. It means that the higher x, the lower y. In this case, you have only positive correlations, meaning that in all these cases, the higher x, the higher y. But we don't know the strength of this connection. It's important to play a bit this game to get used to the correlation coefficient because it's really super important thing in statistics and data analysis. I think it's even like becoming common knowledge now outside of scientific fields, but everywhere in science you face correlation coefficients and you need to have the feeling about them, like you need to understand them. Okay, let's try. I think this one, you can see it's just a cloud of dots, not really much. So I think the correlation is pretty small. Let's say 0.15. No, it was higher. I think it's because of this point. Actually, we have this point here, I think. Next, yeah, we had a point here. It's much higher. Try to guess with me and check whether you was correct or not. I would say that it's something like 0.75. Whoa, I was pretty close. I think this one is even higher, but not that much higher. So I think that it's 0.86. Wow, I was pretty close. This one seems that, remember that you can just divide this table by 4 quadrants. And if you have many dots here and many dots here, they will give like positive value. If you have many dots here and here, you will get negative value. Here it seems like something like 2-to-1, so it's pretty positive, I think. I will say something like that. Yeah, it was almost right. This one is very positive. It's very positive. I would say 1. A bit less, but still very positive. And so on. I can play it actually pretty long because, I'm sorry. This one, I think it's very high. Yeah. Okay, I can play this for a long time, really. So let's go back to R, and we can try to calculate such things in R. So let me share with you a screen for RStudio. So imagine we have these two vectors, x and y. X and y. You can just copy these values. It's like 1, 2, 6, 8, 9, 7, 7.5, 10, 3, 4, 5.5, and so on.
Can you please paste it in the chat?
Sorry?
Can you please paste
Yep.
the value in the chat?
Yeah. Of
Thank you.
course. Yeah, so you can just copy paste it too. So let's see how it looks like, because scatter plots says much more than just looking at numbers usually. So with a simple function plot, if you apply two numeric vectors to this function, it draws a scatter plot, something similar to what we had for the weather correlation game. So value for x is a coordinate for x for the dot, and value from y is a coordinate for y for the dot. And you can see that it's actually
Sorry, you're not sharing the
yep,
screen.
sorry, yes, thank you. Yeah, I forgot to return. Yeah, so yeah, if you do this, if you put inside a plot function two vectors, two numeric vectors, it draws a scatter plot. And for example, if you take a point, coordinates from the point are taken from the corresponding positions from the x vector and y vector. So yeah, so what do you think? What is the correlation coefficient there? Is it big or small? Just try to guess it.
Pretty good, like 0.80.
Yeah, pretty good guess. I think I would say something similar actually. I would say a bit, maybe even more, but yeah, we need to check. So I want to show how to calculate correlation coefficients in R. But first, let's start with a function cov to calculate covariance. Actually, yeah, let's calculate it. So yeah, you get the value. By the way, if you have an interesting fact, what do you think you'll get if you correlate? If you calculate covariation of a variable with itself? So you will calculate cov x and x. Try to guess what we'll get. Actually, you will get a variance. And it's pretty fun fact because actually you can even calculate covariance and variance using a var function for variance, and you'll get exactly the same results. It's fun actually. Yeah, and you know, correlation is something like covariance normalized by the variances or standard deviations. So you get this like covariance of two variables is something like 18, 19, and you want to know, is it big or small? You see that it's positive, but is it something like something around 0, or it's really big correlation? It's big, really big correlation. To understand that, you need to normalize correlation by standard deviations or variances of your variables. So yeah, you can see that you have one variance is 8, another variance is 42. So in this sense, 18 it's pretty big actually compared to these values. So it's comparable. So if you want to calculate correlation coefficients, Pearson correlation coefficients, you need to use, instead of COV function or var function, you need to use x and y. And actually you get that the correlation is almost 1. It's 0.977 and so on. Actually, you can even do statistical testing, null hypothesis statistical testing for correlation coefficients. So what do you think will be the null hypothesis for correlation coefficient? So remember that null hypothesis, it's always about, first it's about parameters. So it's not about the sample, it's about parameters. It's about mu, it's about sigma or whatever, but it's about some global population parameters that we try to estimate. We try to do some conclusions, infer some conclusions based on our data. The second important thing about null hypothesis, it's usually about something that we have, something like that we have no effect in general. So assuming that, what do you think will be a null hypothesis for correlation coefficients?
That there is no correlation.
Exactly, you're correct. It's great quest actually, because yeah, really, null hypothesis for correlation coefficients, that like the real correlation between two variables, assuming that we have only just two samples, but we can sample more samples. So in general, this correlation is 0. So there is no connection between these two variables in real populations. So to test the hypothesis, you need to use the function core test. It's pretty similar. It's pretty similar to how we did core.test. It's pretty similar to what we did with a t-test actually. So instead of t-test, like t-test here, we have core test. And that's all actually. And let's try and run this line. And oh, okay, we have a lot of information, right? Actually, that's pretty similar to what we get when we do t-test. So if you remember, you actually get the t-statistic and degrees of freedom and p-value, and you have confidence intervals, and you have correlation estimate. So first is a correlation estimate. It's the same that we get using this core function. So it's our best estimate of a correlation in two variables in like global population based on our sample. But then we want to do some more conclusions based on our data. For example, we can draw a 95% confidence interval for this correlation coefficient. So how can you interpret this? So you have this interval from 0.91 and 0.99, 95% confidence interval for population, for correlation in the population. How can you interpret it?
That in 95% of all the considered samples will get correlation not lower than 91% and not higher, probably not higher than 99.
No, actually, no. Not like, actually, that's a really complicated question, because confidence interval is really very misinterpreted thing in statistics, and even in some books, like usually for like applying statistics for linguistics or psychology or biology, you can get actually wrong interpretation of confidence intervals. It doesn't mean that if you do it many times, correlation coefficient will be inside this interval. It doesn't mean that you have 95% of values inside this interval, or even it doesn't mean, but it's actually discussed, pretty much debated, that you have 95% of catching real population parameter, because true frequentist statistics guys says like, no, you either catch that or not. So you can say that it's 95% because it's already, there is already population parameter. So the only things that you can say about that, you are 95% sure that it catches the population parameter. So if you if you draw this many times, if you draw this samples many times, in 95% of cases, population parameter will be catched by this interval. So actually what we can say about our population parameter, like correlation, population parameter here, that we are almost sure that it is not zero. So it's, we are 95% sure that it's between these two values. And of course, this interval doesn't catch zero. And that's why we can infer that, yeah, we can make mistakes in no more than 5% cases, saying that real population parameter is not zero. But now let's go to p-value. Remember that if you see something like that, like 2.234e minus 0.7, it means that actually it's very, very small number. E minus 0.7, it's a scientific notation, meaning that actually you have 0.0000007 zeros, and then 2, 2, 3, 4. So actually you can say that if null hypothesis is right, so correlation coefficient in reality, true correlation coefficient, is equal to 0, probability of getting this and even higher correlation coefficient in data sets in like if you sample the data set with the same sample size, is if you get probability of getting this correlation coefficient or even higher correlation coefficient is very, very, very small, because really it's very high correlation coefficient. It's not really, I mean, it's really it will be surprising to get this and even more correlation if actually there is no correlation in population. So yeah, but imagine the situation that we add some another value to our data set. Let's say 150 and 10 to x and y. And now we can plot it. Now you can see that we have something like an outlier here. Imagine we recorded some kind of this strange guy in our data set. And now, what do you think will happen to covariation and correlation coefficients? Actually, this small value really increases variances, especially for x. So now you have like a variance from this, and mean will be somewhere in between, somewhere here. And this one value increase variation really much. And if you calculate the correlation, it will be like really small. It's even negative now. But you know, if you get this small correlation coefficient, you think that okay, maybe it's really something like a 0, because you know, it's very close to 0, and you know that like getting like real 0 in real data, like 0 correlation, like 0, 0, 0, 0, 0, it's very improbable. Actually, it's unreal if you have really continuous data. So what hypothesis can you have here? That maybe it's just like a real correlation coefficient here is 0, and it's something like a noise, you know. And let's see how it actually change our data, change our p-value. So now, if you calculate p-value on Pearson coefficient of correlation, it will be pretty close to 1. So you can see that probability of getting of this correlation coefficient, or even more, in the case that H0 holds, is pretty big. So it means that if you have one such outlier, Pearson's correlation coefficient will actually be broken. So it will not calculate what you want. It will be very biased by this small outlier, actually big outlier, but it's just one, and maybe just some error in the data. So what can you do instead? Instead, you can calculate not Pearson correlation coefficient, but some of the non-parametric analogs of that, called Spearman or Kendall. It's three most famous correlation coefficients: Pearson, Spearman, and Kendall. I think that Pearson is the most popular, then Spearman, and then Kendall. And all of them works in the same fashion. Maximum value for correlation coefficient is 1, minimum value is -1, and no correlation means 0. But calculation inside is somewhat different. Actually, you can think about Spearman correlation coefficient in terms of calculating ranks on the values and then calculating Pearson correlation coefficient. So instead of using this formula with x I minus x minus average of x multiplied by y minus average of y, you calculate ranks for every value. And this means that we'll actually, I don't remember how to calculate ranks in R. I think, is it from sample ranks? Yeah, I think yes. So you can see that, yeah, if you calculate rank on X, you will get, you will change your like intervals in the data and make them like the same. It will be interval 1 for every point. And the most noticeable change is for this value 150, because previously it was 150, now it's just 12. The same you can do for y, but it will not change that much. So rank transformation just makes ranks from the lowest to highest values, and if there are some ties, there are different algorithms that you can apply. So if you do Spearman correlation coefficient instead of Pearson correlation coefficient, it's something like calculating Pearson correlation coefficient on ranked data. So here you can see that this correlation coefficient is significant, and therefore Spearman correlation coefficient is more robust to outliers in the data. And actually, in real situation, I would recommend to try both. If you get the same data, if you get very similar results, it usually means that relationship is linear and you have no outliers. But if you have really different p-values and R estimations for using Spearman correlation and Pearson correlation, it usually means that you need to look more careful in your data. Maybe you have some not linear dependency. I will show you some picture from coefficient. So yeah, you can see here that if you have just something like a cloud of dots, correlation coefficient is pretty straightforward. Like if you have this, something like this, you have like something like 0.8. If they're aligned on the same line, it's 1, and vice versa if higher x means lower y. But if you have some non-linear or even non-monotonic relationships, it will break your Pearson correlation coefficient. For example, something like that. You can find it really often in your data. For example, if you have something like U-shaped relationship, sometimes it's called. For example, if you give some drug to participant, it helps them, but if you give more than optimum dosage, it actually harms them. So, for example, in psychology, there is a law of optimum of motivation. Like if you motivate, if motivation is too high, performance is lower than when motivation is somewhat high. But if motivation is very low, performance is very low too. So it's non-linear, it's non-monotonic. Or it can be even like more complicated. And all the situation cannot be catched by Pearson correlation coefficients. So if you have zero correlation coefficient or close to zero correlation coefficient, it doesn't mean that you don't have any association in your data. It just means that you don't have linear association like that or that or even that. Maybe you have more complicated relationships. So it's very important to remember about this fact. Okay. Okay. And now, also let's check another, the last correlation coefficient. It's based on science. It's a bit less popular than Spearman. And again, you have more or less the same result as for Spearman. So it's another non-parametric analog for Pearson correlation coefficient. And now let's try to delete this outlier and see what will happen to correlation coefficients. So remember that if you have like default one, it's Pearson. You have something like 0.97 and so on. But what will happen if you calculate, for example, Spearman correlation coefficient here? What do you think? Try to guess.
Should be similar.
Yes, right. It will be similar. It will be similar. So see, look at that. You have rho that is 0.96 and p-value is pretty small again. So the formula is different, but the result is very similar. Meaning that, yeah, if you have no outliers in the data, if you have pretty linear connection between two variables, Spearman and Pearson will give you more or less the same results. It's important to understand about them. And Kendall will do more or less the same. Yeah, it's a bit lower, but still p-value is significant. It's very close to zero. Okay, now let's try it on some real data. Let's upload tidyverse and calculate this data set. I will give you the link. Oh, sorry. And remember, if you just run this line of code, you imported data, but it just shows in the console. It was not saved in a variable. So you cannot work with it, because you just imported it without saving to any variable and show to on the screen. It's cool to try it like that when you just download data and try for the first time, but then you need to do something with this variable. So you need to assign the result of this line to some variable. Let's say cool. So let's have a look what we have here. We have some students, the males and females, more males, different races, different school types, and so on. And they have 5 scores: read, write, math, science, and I think social sciences, something like that. And how do you think they are correlated? What do you think? First, let's plot it. Let's say like we'll select columns from read to socaste, read to socaste, right? And then we plot it. Just function plot will do this nice scatter plots for every column with every other column. It's pretty common situation. Good students tend to be good in everything in general. It's actually something that was of particular research interest of Spearman, who introduced correlation coefficients, some correlation coefficients, as you could know from the name of correlation coefficients. And he wanted to study whether there is some common factor that explains some ability to be good in different tests. And he hypothesized that there is something like a G factor, general factor, that makes people good in like every intellectual test. And that was actually something like starting point for IQ testing and IQ measurements, and also for factor analysis method, because he tried to prove it with a mathematical method that we created. He failed to do that, but he created the mathematical method. So you can see that actually every column is correlated with every other column, and all these associations are actually positive, right? So you can see like this oriented clouds, but not like this. So everywhere, the higher X, the higher Y. The higher, in general, grades for reading, the higher grades for science. What do you think? What is the highest correlation here?
The one above science.
And which one?
The one above the science text.
Science and what?
The one above.
Sorry, which one?
The one above. The one.
Yeah. So actually, this scatter plots you can read this way. So every like plot is a scatter plot of the variable from this vertical and from this horizontal line. So, for example, this plot means the scatter plot between science for x and math for y. Actually, it's a really good way to present it, but of course, if you have many variables, it's hard to observe many correlations, and there are actually complicated multidimensional methods that try to solve this dimensionality problem, called dimensionality reduction methods. And actually all these complicated advanced methods, they are based on correlation or covariation matrix. So correlation is very basic thing in terms of statistics actually. So, okay, how to calculate all correlations altogether? It's actually pretty similar, pretty simple. Instead of plot, you just use a function COV to calculate correlation matrix. We'll start with a covariation matrix. So again, for the diagonals in covariation matrix, you have a variance for reading, variance for writing, variance for math, variance for science, variance for social sciences, I think. And here you have covariances. So remember, covariances, correlations is something like covariances normalized by variances. So you can see that the highest value there are usually values for variances, and values for covariances are somewhat lower, but not that lower. It means that in general we have many positive correlations there, and they're pretty big. And to do that, we need to use the core function again, and let's see what we have there. So yes, we have high correlation there. So actually, both covariation and correlation matrix, they're symmetric. So correlation of writing and reading is the same as covariation of reading and writing. The same for correlation. Correlation of writing and reading is the same as a correlation of reading and writing. So this matrix is symmetrical among this line. And yeah, correlation of one variable with itself is one, like the most possible correlation, right? And what is the highest value here? I think it's actually reading and math. And it's somewhat surprising for me actually, because why reading and math? But okay, it's something that comes from data. And you can see that, yeah, it's pretty like, it is less variable than, for example, for social sciences. Actually, it means that this correlation is also depends on variations in data, because, for example, for social sciences, you have bigger variation, bigger variance, bigger variability, like in general. And in general, for social sciences, it means that you have lower correlations. Okay. And now you want to say, okay, I've got these correlations for different variables, but are they significant? But unfortunately, core test function can calculate correlations, can calculate p-value only for one pair. So in this case, you need to have something, some external packages. For example, I really like how it's realized in package psych. Install packages psych, because yeah, in psychology we really work a lot with correlation matrices. So it's installed on my computer, so I don't need to install it, but for you, I think you will need to install it because you didn't install it before, and there are low chances that some other package use this package and you install this package as dependency. So the difference for core test function in psych that here you use core, so 2 R letters. And let's see how it works. You have a correlation matrix, and p-values. And actually, yeah, all of them are zeros because all of them are significant. But you can actually think that, okay, but we have a problem when we have many tests, when we have multiple tests. What is this problem? Do you remember? So if we correlate, like, so imagine you collected many variables, and now you correlate each other to each other, you get p-values and get, for example, in this case, something like 1, p-value is less than 0.05, and you're like, okay, I found something that I can publish. And I have a I have a theory that explains how correlation, how that works, why reading is correlated with science tests for children, and yeah, actually many education studies are filled with this spurious correlations. In this case, you can see that it's not spurious, I think. But what is the problem? Do you remember the topic of multiple comparisons and Bonferroni corrections and so on and so on? So,
yes, the problem is that we have higher probability to obtain significant result when we perform a lot of the tests.
Yeah, even if you don't have any connection. So we have higher probability of higher family-wise error rate. So yeah, in this actually, in this case, it's actually adjusted for multiple comparisons using by default Holm-Bonferroni comparison, but you can, if you want to do some more conservative, you can set Bonferroni. I hope that yeah, just methods maybe. I don't remember. Okay, let me check the help, because yeah, you know, you don't need to learn all you don't need to learn all parameters for all functions. If you're sure about them, you can try, but if you're not sure, you just go to help. And here I can see method is a Pearson or Spearman or Kendall, right? And if I need to specify adjustment for multiple tests, I use a adjust parameter. And if I'm not sure about how to write Bonferroni, I think I'm correct. You can find it in help too. So actually, even Bonferroni corrected p-values are all significant. So yeah, you can be pretty sure that all these values are really correlated. So you can reject null hypothesis about there are no connection between these values. Okay. And there are also two things that I want to show you. One is about tidyverse, about analysis in tidyverse, and another one about one more thing about correlation matrices, and correlation visualization. What do you want more? Okay, let's start with tidyverse thing, because we need to go further with tidyverse, and it's really good data set to show you this thing. So here you can see that different grades are written as different used to the, like, they displayed as different columns. Right, but it's not the only way to represent this data. Imagine the situation that you have, let's do some more simple example. Imagine you have some, let's see, let's create some names. Give me 3 names. Okay, let's do it like that. Tribal, like name before R and after R. And we assume that we recorded for different students weight in kilograms before and after our course. Give me just some name, just whatever name you want. Even your name. Come on, I want to know that you are here. Don't be shy. How?
You can use my name.
Your name?
My name is Natasha.
Natasha, okay. Good. Natasha. Oh, it will be, okay, you can, I need to ask you about your weight. Okay, it will be not you, Natasha, just another Natasha, some imaginary Natasha. And her weight is, let's say, 68 before our course and 62 after our course. Let's create another name. Let's create another student and his name. Come on, don't be shy. Just give me some name. Come on, guys.
Jean-Paul Sartre.
How, sorry?
I will write it down. Okay,
okay,
I don't know, John.
John, okay. Okay, let's do John. John. 79 to 71. And last one? Let's Betty. I don't know why Betty, but I was 83 and 65 for them, right? And you will have this table, like measurement before and measurement after. But you can also have it this table in another way. So let's another Okay, let's save it as a weight. You can have the same data. You can represent in another form. You can you can create a specific column measurement where will be said like before R or after R. Specific column for weight, and you have several. In this case, some name will be repeated several times. For it will be repeated for before R and after R. And to convert between these two types of data, you have functions pivot longer and pivot wider. So pivot longer will make from wide data the long data. And let's see how it works. You apply as a data your data set. For calls, you select your columns that contain some data that you want to make longer after R. Yeah, and I think I forgot one important thing. I need to create also names for new column. Let's say names to time. So it was either before R or after R. And for values, it will be weight. Yeah. So you can see that actually it is the same data, but it's rearranged in longer form. Which form do you prefer actually, longer or wider? So it is a wider, it is a longer. What do you think is better? Write longer if you prefer longer, and write wider if you prefer wider. Or you can explain if you have more complicated answer. Come on, guys, I need your answers. Just to, I mean, what you think is better? Which one is, which one you prefer?
I think that longer is better because in this type of table, we have 3 types of variables, and they all, it's like really easily, for each variable, we have corresponding variables. Yeah, while in the wider table, we like have these variables grouped.
Yeah, actually, yeah, I understand you that actually it's usually easier to process data when they're in a longer form. And many functions and models in R expect that you have longer data set. But some expect that you have wider data. For example, if you want to calculate difference between before and after, it's easier to do when you have wider. Also, it's easier to read the table if it's wider usually. But in most cases, when you do manipulations with data, it's easier to do them on longer data set. It means that you need to know how to convert longer data to wider and vice versa. So I actually showed you this function, pivot longer. It's a function from tidyr package. It's a basic package from tidyverse. And if you want to convert from longer to wider, how do you think it will be the function called? Just try to guess. If you want to do wider table from long one.
Pivot wider.
Yeah, right. Actually, I really like how it's called, because it went from in the previous versions of tidyr packages, the tidyr package, airshape and airshape 2, it was called melt and decast, like melting and decasting, like плавить. I don't know. It was hard to actually learn which one to use, and when I needed to convert from wider to longer or vice versa, I googled my own materials how to do that, because I couldn't remember. It's like remembering in childhood where's the left and where's the right. You know that something is left, something is right, but you need just to remember. Then they change it for gather and spread, and still sometimes used. But now they have pivot longer and pivot wider. It's fantastic. It's really easy to use, and it's really easy to remember. If you want longer, you use pivot longer. If you want wider, you use pivot wider. And that's it. Here, for pivot wider, instead of names to and values to, you need to use parameters names from and values from. Let's see how it works. Names from, and we'll take this this variable time, and values from. We can use square. Sorry, we can use double quote. We can use quotes here, and we can avoid them. But we need to use quote here. It's obligatory, because here we refer to some columns in the data. Here we refer to columns that were not created yet. For more convenience, I will do it like that. I will use quotes here. Because in general, in tidyverse, it's usually assumed that you don't want to write quotes for your columns, and usually can be omitted, but not everywhere. So yeah, and you return from longer form to wider. And now let's go from this very simple data set to our data set. So let's have a look on our data set. So we can think of these five tests as something like a wide data set. And for example, you want to calculate, I don't know, let's say mean and standard deviation for every score. You can just calculate mean read, mean write, mean math, mean science, mean stochastic, and so on. Or you can work with multiple columns. That will be pain in the ass actually, but we can learn it too. But it's actually like a really advanced tidyverse. So if you want to calculate summary statistics for all five of them, it will be hard to do that. You will do many manual typing and copy pasting. So for some tasks, it will be easier to convert it to longer form. And let's see how it works. We'll get school. You need to select, and you will use pivot longer or pivot wider. longer, wider. You want to make this. Like, so we use
maybe
longer,
but because it is because it is wide now. So
yes, exactly. So and now we select these columns for calls. For names columns, we create a column, let's say test, and for values, let's create a score. Great. And now for every student is repeated 5 times. You have some metadata for him, and actually now every line, every row is one measurement. So in both cases you have tight data, meaning that you have one row is one measurement, but you can actually decide what is your measurement. A measurement is one student or one score for one student. In this case, in longer version of this data set, you have one score for one student as a measurement, as a separate row. And in this case, you can easily, for example, combine, if you want to calculate mean scores for all tests, or for example, if you want to even like calculate like mean scores for different races, for different genders, and so on, you can use group by that we studied previous time, group by, let's say test, and then summarize mean score. Let's say test mean score, right? And now we calculated mean score for every test. If you want to calculate mean score for every I know gender, let's say gender, we have gender, or we have gender like this, maybe. Yeah, we calculated mean score for females, for males, for math, mean score for reading for females, mean score for reading for males, and so on. So you can see that now with combine that with a group by and summarize, you can do this summarizing tables, pivoting tables pretty easily. So you change gender to race, for example, and get different, you get mean scores for different races and tests. What else we want to calculate here? What other statistic? What are the statistics you remember actually? Instead of mean, what can we calculate else? Even maybe outside of not from this course, maybe you somehow know other statistics, or you remember some that you studied on the course. Just try to median, exactly, right. So maybe the score is skewed, so it's not symmetrical, and median score will say say to us more than median than mean score, right? And we can calculate it. You can see it's pretty easily can be done. If you have your data in a long format, you can just group by, summarize, and so on. Okay, and then let's return the data from long format to from long format to wide format. Use pivot wider. Names from test values. And we return again to this wide format. Actually, it's very important skill converting to wide data and return to long data and vice versa. That you'll need not only to prepare your data, to pre-process your data for your analysis, but it's also a really cool skill for data manipulation. And it will help you a lot if you master this converting from long to wide and wide to long. And it's really easy to do in tidyverse, as easy as it is possible, because actually it's very complicated operation if you think about it. But with this pivot longer and pivot wider functions, pretty simple. If you don't remember the syntax, just get help for the function in my material, or just Google in the internet. It is I do not require I do not expect that you will learn it today, how to easily convert it and you like remember it, but I expect that you will learn that there are these two forms of data, and there are some kind of like pivot functions that maybe you don't remember, but you can Google them. So if you have this task, you will able to Google and solve it by yourself, maybe after some time. So you can see even me, I do not like remember all details, and I can go to help if I don't remember something. It's pretty okay. But if you understand this idea of longer and wider data, it will ease your analysis a lot. And maybe, okay, maybe I will show you just final thing. I think it will be easier if I show you even actually yes, I will share the screen. There is a nice tidyverse package. I mean, not base tidyverse, but extended tidyverse package core, called core, like with 3 R's. And it's really fun, and it's like nice package to work with correlation matrices that create like nice correlation tables and do not show extra information. And what is cool that it can create even some network graphs for correlation. It's another way to think about correlations, correlation matrices. So, for example, here we can do it. We can do it too. Let's use the function. I think I have this. I think I have this package. Yeah, but if you don't have, you need to install it. Install packages for. I mean, it's really fun to use. And let's take our school.
By the way, your demonstration is frozen now.
I'm sorry. Yeah. Yeah. So you need to install a package core. If you don't have it, I have it because I used it before. And then let's select this variables, and it has a function correlate. Yeah, this function correlate just create a correlation matrix, Oh, it's actually correlation table. And then you let's say not 0.2 but 0.6, right? And you can build a graph based on the correlations. So the tighter the connection and the more blue the connection between two variables, the higher correlation between them. It's just another way to represent multiple variables and correlation between them. You can work with it as it was a graph actually, because you can use it this correlation as a something like a distances for a graph, and you can visualize it as a graph. Actually, this function, this package has a lot of nice things to just make this correlation looks better. For example, I like fashion. Just do it nice. Creates correlation table that actually it is, I think, character columns, but that doesn't matter. If you just write it, it's really easy to read here. Or you can use also shave. I think no, I think we need to just shave and then fashion, right? Yeah, it's the same way I do every morning. Not this morning, but in general. Shave, then fashion. But first you start your day with correlation. Okay, I think that's all for today. I showed you all I wanted to show you for today, and actually even more, because yeah, I think I'm not sure that you'll need this one, this core package, but it's really nice and easy way to work with correlation matrices. It's important that you know how to work with pivot longer, pivot wider in general, and you understand the idea of long and wide data sets. If you need more, I recommend you to read the R4 Data Science book. And of course, we covered how to calculate covariation, covariance, and correlation coefficients, and why sometimes different correlation coefficients show the same, more or less the same results, and why they can differ, what can be cause for this difference. And you know how to calculate it using basic core test function. And for multiple correlation tests, you can use psych package with the function core test that will actually apply also Bonferroni or whatever correction for multiple comparisons if you want. That's all. Thanks for your attention. See you next time. Bye.
Thank you.
Thank you.
Thank you.
Bye.
Bye.
You will download, you will upload the notes
Yep.
to the site, right? Okay, thank you.